Alright, so this lecture is about assignment 1, which I have called Know Your MOSFETs. Alright, so let's talk about knowing a transistor. So for example, if I want to use a particular type of chili in my cooking, I first must know how hot it is before I start using it. Or if I am a race car driver and I'm driving a car for racing, I must know everything about the car before I use that car in a race. Similarly, if I'm going to use a transistor to design circuits, then I must know that transistor. Now, what does it mean to know a transistor? It means to know its parameters. Alright, because the parameters tell us, or we can use the parameters to determine how its current varies as the various voltages are applied. And if we know the capacitances, we can know how fast the transistor will work and so on. And given that, we can use the transistor to design circuits and obtain specific currents or specific voltage gains and so on. Right? So this, as I said last time, I had shown you that BSIM parameter file. So that is a MOSFET you are going to use. So you must get to know your MOSFET before you start using. We are able to use that MOSFET in designing your amplifier circuits. But as we also saw last time, the BSIM3 model has more than 120 parameters. Now it is impossible, especially at this stage of your learning of MOSFET analog circuit design, to get to know these 120 parameters and how they affect the current and voltage. Alright, so we are going to keep it very simple, and we are just going to know the three most important parameters of that MOSFET: Vt, mu Cox, and lambda. And those correspond to our simple MOSFET model. Alright, the BSIM3 model doesn't even have the parameters called Vt. Well, it cannot really, the simple model has them. Alright, and because these will be sufficient for us to do the first round on paper design. So in fact, the way designs will proceed from the second assignment onwards is that you will first do the designs on paper with these three parameters and with the simple mathematical model we have derived. First you will do that, then you will put that designed circuit in SPICE, and then you will tweak it and modify it, because the SPICE, of course, you will use BSIM3, and those results will of course not be the same as the simple model results. So the purpose of this assignment, the first assignment, is to know the Vt, mu Cox, and lambda for the NMOS and the PMOS for those BSIM3 models which you are going to use. Now, one thing we recognize right off the bat is that Vt, mu Cox, and lambda, although we assume them constant in our simple model, in the BSIM3 model, these will all be functions of the various voltages and the length of the MOSFET. So the purpose of this assignment is to understand and kind of get a feel for how Vt, specifically Vt and lambda, are varying with the various voltages and with length. Mu Cox we will assume constant, although it actually is not constant as we have seen before, but we will assume it constant for our purposes. Alright. So let us see how we are going to find the Vt, mu Cox, and lambda for the BSIM3 model that we are going to use. Alright. So here is how we are going to do this. So you will simulate this very simple circuit in SPICE to find Vt and mu and Cox. Right? To take you write a netlist for one MOSFET, connect a gate voltage source. Let the drain voltage source be 0.1 volt, basically a small value. Right? For now, ground the body terminal. And you simulate this. keep the width of the MOSFET equal to 10 times the length. Alright, now so I'm introducing one more SPICE statement called dot parameter. So the dot parameter can be used to define variables which can be used in the rest of the SPICE file. So let's say I have defined a parameter called LEN equal to 180 nano and a WID equal to 10 times the LEN. Alright, so and you put curly brackets around it when you do a mathematical expression. And then in the MOSFET statement, you can put L equal to curly brackets LEN and W equal to curly brackets WID, so that you don't have to keep on changing here. You can just change it here once. Okay. So here is what you'll put this circuit in SPICE and in the netlist. You'll vary VG and plot ID versus VG. So you'll vary VG from probably 0 to 1 volt or 0 to 2 volts. You decide what is required for the purposes, and you simulate it. So you do a dot DC analysis and you plot ID versus VG. Okay. For part of the assignment, you will also be doing this simulation with the source body voltage not 0. Alright, when you have the source body voltage not 0, the way you will do this for the NMOS is you will keep the body always at 0 and you will connect the voltage source at the source node instead of grounding it, and you will vary that source voltage. Alright, positive, that source voltage will always be positive, the body will always be grounded for the NMOS. Alright. So let's say you plotted the ID versus VG. Now what do you expect the ID versus VG to be? We've seen this before. First of all, we have kept VD small, right? VD is 0.1 volts. So the transistor will be in triode for most of the range of VG. So we'll assume the triode region equation. And W by L, you've kept it as 10. VDS is 0.1. So the 10 and 0.1 cancel. So we are left with mu and Cox, Vg minus Vt minus 0.1 by 2, 0.05. So this is the equation you are actually plotting. According to this equation, of course, ID versus Vg must be a straight line, ID versus Vg, with a slope of mu and Cox and an x-intercept of Vt plus 0.05 volts. Unfortunately, I'm sure you remember from lecture 4, slide 9, that the actual IDVG does not look like a straight line. It actually bends over. The actual is the blue. It bends over due to series resistances, as we had briefly discussed. So when you do the simulation in LT SPICE, you will find that the curve looks like the blue curve, whose slope is constantly changing. So now which slope do we use, or which slope do we measure? Alright, it's a question. So what we do is we recognize that, so here, as we had seen before, that this blue is due to, this blue here at the near threshold is due to subthreshold currents, and at a higher gate voltage, the bending over is due to series resistance. So we want to find the slope here, and what we also notice is that the slope here is positive. The slope here, I'm sorry, not positive, it is increasing. The slope is increasing, and here the slope is decreasing. Alright, so in between somewhere the slope is going to achieve a maximum. So we look for that maximum point, and we said we'll use that maximum slope to find our mu or define our mu and Cox. So that's what we'll do. Alright, how do we find the slope? As I had said in the last lecture, LT SPICE allows you to plot the slope. So you do dID of M2, that will plot the slope, and the slope, when you plot the slope, you will see that of course here the slope is 0, then it will go through a maximum somewhere here, and then it will go down again. So you find the point of maximum slope. Alright, so it is all written here. Let us find the maximum slope from spice. Let us call it S max. You also find the coordinates of the point where this slope occurs. So find the Vg at which this slope occurs, call it Vg1. Find the ID corresponding to that Vg, call it ID1. Then we say mu and Cox is equal to S max, alright, the slope. And then we can write this equation, ID1 is equal to S max Vg1, this Vg1, minus Vt minus 0.05, where S max you found from spice, ID1, Vg1 you found from spice, therefore you can find Vt from this method. Alright, so this is the way to find mu and Cox and Vt for the NMOS. Alright, how do we find lambda? So here is the method. So again you keep W equal to 10 times length, keep Vg constant and plot ID versus Vd. Alright, you remember lambda is what? Lambda corresponds to, so in fact let me show you the plot. So lambda corresponds, so this is the ID Vd plot, and the slope of this line in the saturation region is equal to 1 over lambda ID, as we have seen I think a couple of lectures ago. I forget the lecture number, or maybe you've not seen, I don't remember now, but anyway here are the equations. So you know you've seen it in this lecture. Alright, so the drain current in the saturation region we have derived can be written as this. So if we differentiate this or find the slope with respect to Vd, then mu and Cox W by 2L, all this remains the same, and the derivative of this is simply lambda. Now what we do is we again make an approximation. We say, well, let us call this approximately equal to lambda times ID, where this is ID. We are calling this ID. Actually this is ID, including the 1 plus lambda Vd. But we really don't care, assuming that the slope is small. These two numbers are not too different from each other. And so therefore to simplify, we'll say, well, this is approximately equal to lambda times ID. And therefore lambda we can write as 1 over ID del Vd. Alright, so taking ID on the other side, which is equal to the slope of the ID Vd characteristics divided by the ID at that point. Alright, so here for example, if I am asked to find the lambda at Vd equal to 1 volt for this specific plot, then I will find the slope of this line at this point. So that is just the d IDM2, and that slope, I'll also find the value of the drain current at that same point, which is 1.1 milliamps, and that slope divided by the drain current will give the value of lambda at that point. Alright, so that is how one finds lambda. And as I said before, lambda varies with Vd and Id and L in the BSIM3 model. Therefore, you are going to find lambda for various values of Vd and various values of L. Alright, so this describes to you how to find mu, Cox, Vt and lambda. Vt will be a function of, let's go back, Vt will be a function of the source body voltage, as we have seen. Therefore, you will also be finding Vt for various values of the source body voltage. The method is the same. You will just put a source voltage here instead of grounding it. Alright. Now let me make a couple of comments about the PMOS. So the method for finding the mu, the Vt, mu, Cox and lambda for the PMOS is the same. You plot ID versus Vg, find the point of maximum slope, that slope becomes mu Cox, and then the coordinates of that slope will give you an equation for Vt, and you will get Vt. And for lambda, you will plot ID versus Vd, and then find the slope in the saturation region, and then find lambda from that slope and the value of the drain current at that point. But because all polarities are reversed in PMOS, it is a little more tricky to determine the circuit that you will use to find all these three parameters. And I am leaving it to you to figure out that circuit. You just have to think for 10 minutes about what you're going to vary and what you're going to keep constant, etc., etc. All right, I think you should be able to figure out what circuit you will use. All right. Okay, now a little about assignment 1 again. So, okay, so I've created an assignment 1 on LMS, which gives a very brief instructions and description. Actually, everything that is there, I'm going to tell you right now. It has a link. The assignment has a link to the assignment statement. There is a PDF file here in this assignment 1. That PDF file has a link to a shared Excel file. I'll show that file to you in a minute. The assignment submission will involve your calculating the VT, mu, Cox and lambda for specific conditions, which I'll tell you in a minute, and then filling up that shared Excel file, and then downloading that Excel file and then submitting that Excel file. The assignment is due at 9 a.m. on Wednesday, 16 September. So let me show you that Excel file. So this is the Excel file. So I have already uploaded. It has two sheets, one for NMOS, one for PMOS. It has a value of mu and Cox. It has, so ignore the orange or whatever color this is for a minute. So you're going to, that orange is what you are going to determine. So you're going to determine the threshold voltage of the NMOS and the PMOS for these values of the channel length. So a large number of values of channel length. You're also going to determine the threshold voltage for various values of channel lengths for various values of VSB, the source body voltage. And you're going to determine the value of lambda for a large number of gate source voltages and drain source voltages and fill up this table. All right. So the length, drain source voltage, gate source voltage. Now let me talk about these numbers, these orange numbers. These orange numbers are the last 3 digits of your roll number. All right. So there are 21 of you, and these last 3 digits correspond to your roll number. Now your assignment is to fill up only the fields that have your roll number. All right. So if your roll number, the last 3 digits are 002, this is the value you have to find. This is the value you have to find. And these, the first row, are the values you have to find. For NMOS and for PMOS. PMOS is the same. This is just a copy of the NMOS, only the voltage is this is VSG, VSD, etc., etc. Otherwise, it's the same. If your roll number is 511, then you'll fill up this value, 511, this value. So 1, 2, and this whole row, 511, whole row, 3, 3, 6, 3, 9 to 11, 13 times 2, 26 values you have to find. All right. And this is a shared Excel file on the Microsoft, the OneDrive cloud. So all of you can fill up only, so replace your roll number with the actual value you have found. So by the time the deadline has come for the assignment, all these fields should be filled out by the respective roll number student, and then that file will be available for all of you. Yeah, now this file is very important because this is your MOSFET. This is, you are going to use this information in these tables extensively when you design the circuits for your second, third and fourth assignments. This is your knowledge. This is your knowing your MOSFET. The other thing I wanted to say is, in the past, I used to have students. Each student fill out this entire file, and they had to do hundreds of simulations. Now I am being a little more kind to you and I am asking you to fill only one row of this table. In the past they had to fill all the rows. Alright, so your work is much less. Of course, the other reason I am doing this is that therefore now your work is unique. Nobody else is finding the numbers that you are finding. Except mu n Cox and mu p Cox, which I have put only one mu p Cox, one mu n Cox. So what I have written in the assignment is, whoever does this assignment first, let him or her fill up this number, and the rest of you, when you do it, you just check and verify that that number is correct. All right, everything else is unique. All right. If you do have any questions about this, maybe you will have, we'll discuss it in the Friday class. All right, so that is the end of this lecture. Next lecture, we'll actually start the DC analysis of MOSFET circuits.